Modern AI systems display an impressive level of surface competence. Models like OpenAI's GPT-5.6 and Anthropic's Claude Fable 5 write production software, summarize scientific literature, and generate fluent text across dozens of global languages. Yet these same models fail a strict structural test regarding the languages they are currently generating. The test involves recovering an operating alphabet. This is the complete, finite set of foundational units, like letters or syllables, used to construct a written language. English uses its 26 letters. Mandarin uses a bounded set of legal pinyin syllables. This chart shows the L26 benchmark results, measuring a model's ability to output complete alphabets. Models score a perfect 26 out of 26 for English and 22.6 for Mandarin Pinyin. But Bantu languages drop off a cliff. Kinyarwanda falls to 10.4 and Bemba to 5.1. These models write convincing, grammatically correct sentences in Bemba, yet they cannot output the exact, finite inventory of syllables required to build those sentences. Generating plausible statistical patterns is distinct from mastering the exact boundaries of a language's closed generative system. The dominant assumption in AI engineering is that scaling up unstructured training data causes an LLM to automatically discover underlying structural boundaries. Massive unstructured text corpora provide volume, but they do not inherently declare where the foundational boundaries of a system begin and end. The English and Pinyin alphabets are declared knowledge. Humanity explicitly identified and formalized these standards, publishing them in children's books and software documentation throughout the model's training environment. Discovered structure is a harder task. It requires a model to infer the finite, hidden rules of a system solely from raw, noisy evidence. Models succeed on English because the alphabet was declared for them. They fail on Bantu languages because those foundational inventories were rarely published as a single, calibrated standard. To succeed, the model must discover the structure from raw text. Unstructured scaling yields fluid approximations of language. It fails to map strict, bounded structural knowledge that was never explicitly written down. The L26 benchmark tests this under a blind condition. The model must output a language's full finite unit list without any external standard provided in the prompt. The scoring is deterministic. The final score is based on a 26-point scale, multiplied by the model's recall and its precision. For a Bantu language, the target is a full syllable inventory, the complete closed set of legal syllables from which the language operates. The recall penalty triggers when the model omits valid, native foundational units. The precision penalty triggers when the model hallucinates or invents syllables that do not actually exist in the language to pad its answer. GPT-5.6's score of 3.1 on Bemba reflects a profound failure. After accounting for missing and invented units, its performance is comparable to knowing only 3 letters of the English alphabet. Scaling actually worsened this specific problem. GPT 5.5 averaged an 11.8 on blind Bantu evaluations. The more advanced GPT 5.6 dropped to a 6.7. More parameters and longer contexts amplify corpus noise. They do not magically write a missing foundational standard that was never present in the training data. The massive, raw text corpora used to train all of these frontier models are fundamentally contaminated and messy. Mapping this data requires an architectural split. The total syllable inventory equals the native syllable inventory plus the augmented syllable inventory. The NSI represents the historical, core structural foundation of the language. The augmented syllable inventory provides the extra units needed for foreign names, scientific terms, or borrowed words. Because LLMs rely on statistical frequency, a common foreign name can trick the model. It sees the frequency of an augmented unit and incorrectly treats it as a native foundational unit. Historical colonial spellings, transcription errors, and code switching further obscure the native system for a frequency-based model. Counting string frequencies predicts the next word in a sentence. It fails to infer the operational bounds of a system. The L26 benchmark includes a control test to see if the models are actually capable of using a foundation once they have one. This is the scaffolded condition. The model is explicitly given the calibrated, correct, full syllable inventory directly in the prompt. Providing the explicit standard causes a dramatic shift. Look at the comparison between the blind evaluation on the left and the scaffolded evaluation on the right for Claude Opus 4.8, Grok 4.5, and GPT 5.6. In the scaffolded condition, the failures nearly vanish. The models use the supplied foundation to achieve near-flawless 26 out of 26 scores. A capability problem occurs when a model receives the complete structure but still lacks the reasoning power to execute the task. An infrastructure problem occurs when the model executes the task perfectly, but only after the missing structure is supplied. These results identify an infrastructure problem. The models already possess the reasoning required to work with these foundations. They simply lacked the foundation itself. A full syllable inventory is curated, version-maintained infrastructure. It is a standard that organizes and constrains the dataset. Frontier models have the ability to use a foundation perfectly. They currently lack the ability to discover it independently. Discovering hidden linguistic rules is a local version of a much broader challenge in the pursuit of artificial general intelligence. Demis Hassabis proposed a test. Could a machine arrive at general relativity using only the raw observations available to Einstein before the theory was published? The restriction is the key. The AI cannot read the final equations and repeat them. It must independently reconstruct the hidden theory from the evidence. The L26 benchmark applies this restriction to language models, asking them to reconstruct an operating alphabet solely from noisy corpus evidence. There are two distinct paths for development. Declared knowledge flows easily from textbooks to model success. Discovered structure hits a chaotic bottleneck of raw evidence, resulting in model failure. True AGI requires the capability to infer hidden generative rules from noisy evidence. It must move beyond merely retrieving humanity's pre-existing formalizations. AI frontier laboratories must move beyond relying solely on unstructured data for non-Western languages. They must explicitly integrate version-maintained full syllable inventories directly into the model training stack. Integrating these foundations provides cascading benefits, improving speech recognition, spelling validation, and dataset auditing across hundreds of languages. Current industry models rely on memorizing declared structures. They struggle when attempting to assemble a coherent system out of chaotic data fragments. This is a direct challenge to companies like OpenAI, Anthropic, and Google DeepMind. The research goal is now to develop models that independently discover a system's boundaries from raw evidence alone. Before these systems are ready to discover novel laws of physics or biology, they must prove they can objectively discover the exact operating alphabet of a language they already speak.